Once again, welcome back to our course. Just now, we discussed in detail about the concept of time constant, and I told you that time constant is nothing but a time taken by the response of a system to reach 63.2% of its final value. And finally, we conclude that if the time constant of a system is more, that means the response of the system is sluggish, and if the value of time constant is low, then in that case the response of system is fast. And we have considered two different cases. In case one, the system time response is small, that is t1, or time constant is small, that is t1. And in case 2, the system time constant is t2, where t2 is more than t1, or you can say t1 is less than t2. So the moment the value of time constant is low, automatically the response of the system is fast. See here, this system 1 will take less time to reach final value as compared to system number 2. That is very important. So by controlling the value of time constant, we are in a position to control the rate of response of that particular system. That is very important. So so far in this course we discussed in detail about what exactly the time response analysis of a system is, and how to find the time response analysis for first order control system. So what is first order control system? It is nothing but the highest power of s available in the denominator polynomial function, or it is simply how many number of poles are associated with that particular system that indicate the order of that particular system. When I say that the order of a system is 1, that means it has only one pole. It may possible that the pole is available at origin, or it may possible that the pole is available at any complex frequency, but the thing is that that system have only one pole. In the same way, suppose we are dealing with second order control system. Second order control system. That means that particular system has two poles which are available or which are associated with that particular system. It may possible that they are available at origin or at any other value, but the thing is that that system has two pole. That is important. That's why the system is called as second order control system. And what are the steps that we need to implement in order to find the time response of any system? The thing is that first we need to obtain the transfer function of that particular system. That is important. Once you know the transfer function, then we try to find out the response, which is nothing but C of S. After that, we try to find the response in time domain by applying a simple logic, that is Laplace inverse of C of S. That is very important. And if you know the value of this C of t, then by applying the logic like CSS of t is nothing but the portion of the total time response which is available at t tends to infinity. That means limit t tends to infinite of C of t. And once you know the value of CSS of t, once you know the value of C of t, then it is very easy for us to find Ct of t. The thing is that we need to subtract this CSS of t by C of t. You will get Ct of t. That's it. So if you are interested to find the response of the system, first obtain its transfer function. Second, obtain its response in frequency domain by considering suitable input, maybe say step, ramp, parabolic, or impulse. Then apply the logic to calculate the value of response in time domain by taking inverse Laplace of C of S, and then we can easily bifurcate them into two portions like steady state response followed by transient response. That is important. Now, let us try to find the time response analysis for second order control system. Now, here, this second order control system, that means this particular system has two poles. That's why the order of the system is second. Now, let us try to take the general block diagram representation for second order control system. Now, this indicates the general block diagram representation for a negative feedback second order control system. Here, this omega n square divided by s in bracket s plus twice zeta omega n. This indicate the forward path gain, which is nothing but g of s, and here the feedback path gain h of s is nothing but 1, and here we have taken a negative feedback system. That is important. So this is the general block diagram representation for second order control system. Now, what we need to do? We have to first calculate its closed loop transfer function or overall transfer function. That will be our first step. So it will be like g of s upon 1 plus g of s into h of s, where the expression for g of s is omega n square upon s in bracket s plus twice zeta omega n, and h of s is nothing but 1. So if you apply that logic, that means by applying elimination of closed loop that we have learned in case of block diagram reduction technique, so we can write overall transfer function, which is nothing but c of s by r of s is going to be equal to g of s upon 1 plus, because it is a negative feedback system, g of s into h of s. Now g of s is this entire term and h of s is nothing but 1 because it is a unity feedback system. That's it. So if you apply that logic, solve, you will get this as an answer. So equation number 1 indicate the overall transfer function of second order control system. Now if you see this denominator polynomial function, here the highest power of s is nothing but 2. See, here we have 2. That's why it is second order control system. I hope this point is clear to everyone. Now here in equation number 1, we have added some new terminology that we have not learned so far, and I hope uh, if you have learned this course in your regular BTech curriculum, maybe for electrical or electronic communication engineering students, you know that this omega n is known as undamped natural frequency, and the unit is radian per second, and zeta is called as damping ratio. Now these two terms are very much important to define the behavior of system. First one is omega n, undamped natural frequency, and second one is zeta, it is called as damping ratio. That is important. Now the time response of second order control system we can identify. The step is, first we need to calculate transfer function, that we have done. Second thing is we need to calculate the value of c of s, but for calculating c of s we need to consider that what type of input we have taken as an excitation. That means we need to take the value of what? R of s. Now here we have decided that the kind of input that we are going to take to uh, check the response of system is nothing but R of s, which is going to be unit step. So in unit step, the value of R of s is going to be 1 by s. That is important. So for unit step input function, you know that the value of R of s is going to be 1 by s. So we can put this r of s as 1 by s. That is important. And this 1 by s we are going to put over here. And let us try to calculate for c of s, response in frequency domain. So by substituting the value of r of s, and if you try to calculate for c of s, it will be like equation 2. Now, in order to calculate c of t from c of s, we need to apply inverse Laplace transform. We can write this c of t as Laplace inverse of c of s. That is important. But it is very difficult for us to find its inverse Laplace directly. So what we need to do, we need to first convert them into some standard form. So rewriting the term like this, s plus zeta omega n whole square plus omega n square in bracket 1 minus zeta square. Yes, we can write this. The thing is that take pen paper, try to rearrange the term, you will get this. That means ये इक्वेशन लिखना क्या, ये इक्वेशन लिखना क्या, एक ही बात है. But why we have writing this? Because straight away we want to take inverse Laplace and we want to arrange them into some standard formula so that we can at the last write their direct formulas in terms of time domain. So the modified version of equation 2 is given like this. I hope this is clear to everyone. If not, you can take pen paper, try to solve this equation by your own. You will get this as the modified version of equation number 2, which is c of s equals to 1 upon s omega n square whole divided by s plus zeta omega n whole square plus omega n square in bracket 1 minus zeta square. That is important. Let me check. There is a problem from my side on internet connectivity. Wait for a minute. Okay. So this is what the modified version of equation number 2. Now, by applying partial fraction technique, the right hand side of the above equation, that means now we are going to apply partial fraction technique and we are trying to again convert them into some more simplified version. How to do that? So we can make the necessary arrangement over here by applying a upon s plus bs plus c upon the entire bracket. If you apply partial fraction technique, you will get this as an output. Now in this case, this term, which is nothing but omega n square root 1 minus zeta square, we are going to denote by some other terminology, which is nothing but omega d. This is called as damped frequency of oscillations, omega n under root 1 minus zeta square, which is nothing but omega d. Okay. So if you put omega d is omega n under root 1 minus zeta square, you will get this as an output, or again modified version of equation number 2, which is c of s equals to 1 by s minus s plus twice zeta omega n whole divided by s plus zeta omega n square plus omega d whole square. Now, by rewriting above equation, we can again make some necessary changes over here. The thing is that why we are making these changes now? Because we want c of t, which is nothing but Laplace inverse of c of s. Because this is very difficult to apply Laplace inverse. That's why we are making the changes so that we can ultimately get the expression into some standard form so that we can get the Laplace inverse directly. That's it. That is the whole agenda over here. So take your time, understand these things, because it is simply the applications of mathematics in control system. So we have equation 2, we modified that equation into some form, then we apply partial fraction technique to convert them into some other form, and then we are rearranging the terms so that we can have some standard formula so that we can apply Laplace inverse directly. Please note down this, take your pen paper, You will get this equation. I hope everybody got this equation. C of s is nothing but 1 upon s minus the entire term. If you are done with this, you can reply in the chat box so that we can move ahead. See, in this case, our objective is we are trying to analyze the time response of second order control system. When I say second order, that means in the denominator polynomial function, we have highest power of s is 2. So here first we have determined the time transfer function of the system, and then we decided what type of input we have taken as an excitation. So in this case we have taken unit step, so r of s is 1 by s, and then we have calculated the expression for c of s. And then in step number 3 we need to calculate c of t, which will be Laplace inverse of c of s. But it is very difficult to find the Laplace inverse of c of s the way it has with us in equation number 2. That's why we are trying to find out some standard form. So by taking Laplace inverse on both sides, now this equation, let's say this is say intermediate equation, say x. Now this equation x is a kind of equation to which we can apply Laplace inverse directly. The moment we take Laplace inverse of c of s, now this is going to be small c of t. So here this is one term, this will be the another term, and this will be the another term. So individually we need to take Laplace inverse of these three terms. So if you apply that logic properly, take the Laplace inverse, you will get this as an output, which is nothing but c of t equals to 1 minus e to the power zeta omega n t cos of omega dt plus zeta omega n omega t into sine omega dt. Or because we know that this omega d, which is nothing but damp frequency of oscillation, is nothing but omega n under root 1 minus zeta square. So this omega n get cancelled. See, this get cancelled. You will get this as an answer. That is important. So this c of t is nothing but 1 minus e to the power minus zeta omega n t upon 1 minus zeta square in bracket square root 1 minus zeta square cos omega dt plus zeta sine omega dt. This will be the equation. This is not the final equation. This is the intermediate equation. Again, we can take some sine, cos, common and all by applying that proper technique. So here I can write sine phi. Now from where I got this triangle, that I'm going to tell you in the coming session. But for time being, let us consider that we have a triangle of base zeta, and then height is square root 1 minus zeta square. The hypotenuse will be 1, and this is nothing but phi. So from this we can write sine phi is square root 1 minus zeta square, and cos phi is nothing but zeta. So if you apply that logic, we can remodify this equation like this. And finally, we can write phi as tan inverse under root 1 minus zeta square by zeta. And this is what the final equations we got. C of t is nothing but 1 minus e to the power minus zeta omega and t upon under root 1 minus zeta square. Then sine of this entire term is going to be your angle. That is omega and under root 1 minus zeta square into t plus tan inverse under root 1 minus zeta square by zeta. This is very important, and this equation you have to remember. This is the final time response of second order control system. The thing is that we just apply the mathematical functions over here and solve them one by one. We will get this as a final output equation. That's it. So I want everybody to please note down this equation. C of t is nothing but 1 minus e to the power minus zeta omega and t upon 1 minus upon under root 1 minus zeta square. Then sine of angle. So sine of angle is omega and under root 1 minus zeta square into t plus tan inverse under root 1 minus zeta square by zeta. That is important. You can also write this equation like this: omega n under root 1 minus zeta square as omega d into d. See this equation. So either you remember this equation or you remember this equation. It's up to you. But if you have to solve numerical on time response analysis of second order control system, you have to remember this equation. That is important. 1 minus e to the power minus zeta omega and t whole divided by square root 1 minus zeta square into sine of omega dt plus this term is nothing but your phi. This is nothing but phi. Your phi is nothing but tan inverse under root 1 minus zeta square by zeta. That is important. If you have done with this, now we are going to understand the most important theoretical aspect, where we are trying to understand what is the effect of zeta on the performance of second order control system. And on this theoretical topic, you may have various types of numerical on gate, maybe for electrical as well as for electronics and communication engineering students. You may have some theoretical type questions, you may have some numerical type questions on this particular topic. That means, what is the impact of damping ratio, it is nothing but zeta, on the performance of second order control system. That means if you change the value of zeta, maybe from 0 to 1, if you put the value of zeta as 0, if you put the value of zeta as 1, or even if you increase the value of zeta above 1 to say infinite, or if you put the value of zeta below 0, say negative, then how that zeta is going to change the performance of second order control system, that we are going to learn. So the general expression for the transfer function of second order control system is given by, we just derive this expression, C of s by r of s is nothing but omega n square upon s square plus twice zeta omega ns plus omega n square. Let this will be your equation number 1. Now in this equation, the denominator polynomial function is also known as characteristic equation, and it is given by s square plus twice zeta omega ns plus omega n square, and that is equated to 0. I told you that the denominator polynomial function of transfer function is also known as characteristic equation. Characteristic equation. And through this characteristic equation, we can identify the response of the system. We can identify the performance of the system. If you equate this particular term to 0 and try to find out the value of complex frequencies, those complex frequencies are called as poles of the system. So characteristic equation plays a very important role to analyze the performance of second order control system. So the characteristic equation for second order control system is this, which is nothing but s square plus twice zeta omega ns plus omega n square. Now what we are going to do, we are going to find the roots for this characteristic equation. The roots for this equation will be like this. Again, it is nothing but your equation. You can find the roots like minus b plus minus your under root b square minus 4ac upon twice a. So if you apply that logic, you can find the roots for this equation. It will be like s1 s2 minus zeta omega n plus minus j omega n under root 1 minus zeta square. So from this equation, if you apply the logic of mathematics, you can find out the roots for this equation, and it will be like minus zeta omega n plus minus j omega n under root 1 minus zeta square. So basically it has two roots. First one will be your minus zeta omega n plus j omega n under root 1 minus zeta square, and second will be minus zeta omega n minus j omega n under root 1 minus zeta square. That's it. Now, in that expression, suppose if you take zeta omega n as alpha and omega n under root 1 minus zeta square as omega d, so the roots for the characteristic equations will be like minus alpha plus minus j omega d. I hope this point is clear to everyone. So here, to find out this, we apply the simple logic roots of the quadratic equations, like minus b plus minus under root b square minus 4ac divided by twice a. That formula we have implemented to find out the roots of that equation. That's it. So here the thing is, we indicate alpha as zeta omega n and we indicate omega d as omega n under root 1 minus zeta square, where omega n is natural frequency of oscillation, zeta is called as damping ratio, and omega d is damp frequency of oscillation, that we already known. Okay, now here we have introduced one more term, and that is called as alpha, where alpha is nothing but the product of zeta and omega n. Now what is zeta? Zeta is damping ratio. And what is omega n? Omega n is natural frequency of oscillation. So the product of damping ratio and natural frequency of oscillation is known as damping factor. Sometimes this is also called as damping coefficient or damping constant. So in gate, it may possible that you may have a question like, what is the damping coefficient of the system, or what is the damping constant of this system? The thing is that you need to calculate the value of alpha, which is nothing but simply the product of zeta and omega n. The thing is that if you know the second order, if you know the transfer function for second order control system, compare that with the standard form, find out the value of zeta, find out the value of omega n, multiply them, you will get the value of alpha. That's it. So these points you have to remember. What is alpha, what is zeta, what is omega n, and what is omega d. Now, this S1 and S2 indicates the roots of the characters equation for second order control system. Let that will be equation number 2. Now suppose we want to indicate them on pole 0 plot. So it will be like this. So x-axis indicate real part, y-axis indicate imaginary part, j omega term. So because it has a real part as well as imaginary part, so real part is minus omega n, which is nothing but minus alpha. So this indicate minus alpha, and it has two imaginary part. First one will be your plus j omega d, and second one will be your minus j omega d. So first one will be your plus j omega d, and second one will be your minus j omega d. So this will be your first pole, and this will be your second pole. Why we have indicated them by cross sign? Because they are indicating the pole now. Because S1, S2 are nothing but what? Roots of characteristic equation. What is characteristic equation? It is nothing but the denominator polynomial function. When you equate that term to 0, whatever the solutions of S you are getting, those are nothing but poles. Hence, for second order control system, S1 and S2 simply indicate the poles. So one pole is available at this location and another one will be available at this location. That's it. Now, let us try to have some imaginative part over here. Now see, this indicate the first pole. Okay, so with respect to origin, the height and the width are indicated over here. This portion indicate your omega d, where omega d is omega n under root 1 minus zeta square, and this portion indicate your alpha, where alpha is nothing but zeta into omega n. So let us try to focus on this particular triangle only. So basically we have a triangle like this. The height of this triangle we indicated by symbol omega d, which is omega n under root 1 minus zeta square, and the base of this triangle we indicated by symbol alpha, which will be zeta into omega n. Okay, and the resultant of these two will be your how much? If you try to calculate, it will be like this square plus this square. You will get the answer. Okay, it will be like omega n. See, if you try to calculate the value of hypotenuse, it will be like this square plus this square. So it will be like omega n square in bracket 1 minus zeta square plus omega n square zeta square. If you solve, you will get here as omega n square. If you take square root, you will get omega n, which is nothing but over here. That means the distance of pole with respect to origin is nothing but omega n. That is important. See, same thing is mentioned over here. This is nothing but omega n. And now in this triangle, if you divide all the three sides by a same factor, which is nothing but omega n. See, if you divide all the three sides of triangle by omega n, so this omega n cancel, here this omega n cancel, and here this omega n cancel. Now again you have the triangle where base is zeta, height is 1 minus zeta square, and this is going to be 1. This is called as phi, which is very important. The same triangle we have considered in the previous slides, and I told you that I will inform from where we got this answer. Actually, that triangle we have plotted by plotting the poles of second order control system in S plane. And by applying this logic, we came to know that what is the relationship between zeta, then under root 1 minus zeta square, 1, and then phi. And from that we write that equation phi is nothing but tan inverse square root 1 minus zeta square divided by zeta. That is important. See, this is very important. So now let us take the cases one by one, because in this case our objective is we want to analyze that how the response of system is going to vary when we change the value of damping ratio, that is nothing but zeta. So case number 1, if you take the value of zeta from 0 to 1, then what will happen? So we know the roots of second order control system. It is like minus zeta omega n plus minus j omega n under root 1 minus zeta square. Now see here, the moment you put the value of zeta in between 0 to 1, that means the value of zeta is not 0, it is not 1, it is between 0 to 1. More than 0, less than 1. Hence, this particular square root is going to be always positive. That means it has plus minus j omega n term in picture. So, I can say that the roots of the characteristic equations are complex conjugate with negative real part. I hope this point is clear to everyone. Why we have written this statement in this case? Because the value of zeta is in between 0 to 1. The moment we put the value of zeta in between 0 to 1, the roots of the characteristic equations are complex conjugate with negative real part. And the response, or you can say the location of these poles on the pole 0 plot will be like this. So one pole will be available at here, another one will be available at here. See, this is nothing but your alpha, and this term will be your omega d. So it will be like minus alpha plus minus j omega d. So one pole is available at minus alpha plus j omega d, which will be this one, and another pole is available at minus alpha minus j omega d, which will be this one. That's it. I hope this point is clear to everyone. Now in this case, the response of the system is said to be underdamped. That is very important. Now why the response is underdamped? Because see, the value of zeta is less than 1. Hence the system is underdamped. And the response oscillation will be like this. See, initially, the moment you have not applied any input, output is going to be 0. The moment you apply step input, in this case, output goes on increasing like this. And it will try to oscillate with respect to its desired value. and based on the damping, it is going to finally reach to its final value. That is important. And the system is said to be stable. See why it is said to be stable? Because the oscillations are continuously goes on reducing. They are die outing. They are going on reducing. That is important. So this is very important. This is the case 1. That means when the value of zeta is in between 0 to 1, the roots of the characteristic equations are complex conjugate with negative real part. The response of the system is underdamped and the system is stable. So I want everybody to please note down this point. This is very important. And based on these cases, you may have various types of numerical in any competitive exam. It is not at all necessary that we always need to focus on gate. It may possible that you may have questions in MPSC or UPSC or even in IES, or even if you are preparing for state government exams like Mahatransco, Mahadisco, Mahagenco, or even for some other competitive exams. This portion is very important. Effect of zeta on the performance of second order control system. And this is the case 1 where we have taken that if the value of zeta is in between 0 to 1, what will happen to the location of poles of second order control system in pole 0 plot, and how the response of the system is going to be there. Please note down this. This is very important. So once you are done with this, let us take case number 2, where suppose if you put the value of zeta as 1, then first thing, what will be the nature of roots of characteristic equations, or what will happen to the poles of second order control system? The moment you put zeta equals to 1, this is the general expression for the poles of second order control system. Now put zeta equals to 1 over here. The moment you put zeta equals to 1, this term is going to be 0. So in that case, the poles of second order control systems are real, they are negative, and they are going to be equal. I hope this point is clear to everyone. See, put zeta equals to 1 over here. This term is going to be 0. So it has only real part. So the roots of the characteristic equations are real, both are negative, and both are equal. And their locations in the pole 0 plot will be at this particular point. This is the general representation, but ultimately all are equal, all are negative, and all are real. That is important. And in this case, the response of the system is critically damped. This is very important. And suppose if you are interested to find out how the output is going to vary with respect to time, so it is like this. This is the critical response. Why? Because here we have taken the value of zeta as 1. So when the value of damping ratio is 1, the roots of the characteristic equations are real, equal, negative, and the response of the system is critically damped. That is important. Please note down this. These points are very important. I hope this is understood by everyone. If you are done with this, please reply me. So this is case 2 when we have taken the value zeta as 1. And the system is absolutely stable. Why is stable? Because the response is approaching towards its desired value, final value. That is important. So first case, we have taken the variation of zeta in between 0 to 1, not exactly 0, not exactly 1. And in case 2, we have taken the value zeta is exactly 1. And we came to know that the roots are real, negative, and equal. The response is critically damped and the system is stable. Now, let us take case number 3. What will happen if you increase the value of zeta more than 1? So first, let us try to examine that in this particular case, what will the nature of roots of characteristic equations. So this is the general expression. Now put zeta more than 1 over here. Suppose if you put zeta equals to 2 over here, the moment you put zeta 2, it will be 2 square, that will be 4. 1 minus 4, it will be square root of minus 3. Or I can write this as square root of minus 1 into square root of 3. Square root of minus 1 will be your j. So already we have j component over here. So this j multiply, it will get minus 1 into square root of 3, that will be 1.7321. So ultimately, if you apply that logic, you can find out that in this case, the roots of the characteristic equations are real and different. That is important. Both the roots are real, that is sure, because here we don't have imaginary term, because here we have one more j term, j multiply, it will be minus 1. So the roots are real and different. And if you try to locate them on S plane in pole 0 plot, it will be like this. One will be available at this location, another one will be available at this location. Why I have indicate them by cross? Because they are poles, and I told you that poles we are always going to represent by cross sign. That's why they are indicated by cross. Okay. Now in this case, the response of system is overdamped. Why it is overdamped? Because the value of zeta is very much high as compared to 1. It is more than 1. The moment you take the value of zeta more than 1, damping is more. That's why the response is overdamped. That is important. And the response is something like this. See, it is slightly sluggish. Initially, when you put the value of zeta equals to 1, the response is critically damped. And the response is something like this. Like this. The response is fast. That means the response is quickly reaches to its desired value because the value of zeta is 1, critically damped. But because in this case the value of zeta is more than 1, the system response is sluggish. That is important. But the system is stable. Why? Because it is approaching towards its desired value. See, it is reaching to its desired value. That is important. So please note down this. Case number 3. when the value of zeta is more than 1. So we are learning what is the effect of zeta on the performance of second order control system. So case 1, when we have taken the value of zeta in between 0 to 1. Case 2, when we have taken the value of zeta exactly 1. And in case 3, we will increase the value of zeta more than 1. The response is overdamped, but the system is stable. Response is slightly sluggish. And in case 1, when we have taken the value of zeta less than 1, but it is more than 0, so it is like this, oscillatory, like this, and then finally approaching to its desired value. This is case 1, this is case 2, and this will be your case 3. So if we are done with this, let us try to discuss next case. It will be case number 4, in which we are going to put the value of zeta exactly equals to 0. So the moment we put zeta equals to 0, what will happen to the locations of roots of characteristic equations for second order control system? See, the moment you put zeta equals to 0 over here, this term is going to be 0. Now in this case, the nature of roots of characteristic equations will be complex conjugate with 0 real part. That means they don't have 0, they don't have real part. Real part is going to be 0. So in this case, the roots of the characteristic equations, or you can say the poles of the systems, are going to be like complex conjugate with 0 real part. That is important. They don't have this particular term into picture. This term is going to be 0. Their locations on the S-plane in pole 0 plot will be like this. One will be available at plus j omega, another one will be available at minus j omega n. That is important. Now in this case, the response of the system is said to be undamped. Why undamped? Because there will be no damping ratio. There will be no factor which is responsible to die out the oscillations which are generated by the system during its transient period. So the response of the system is undamped, and the response is something like this. That means the variation of output with respect to time when it is provided with some excitation, which is nothing but unit step. So it will be like a oscillatory in nature with constant magnitude, neither increasing nor decreasing. So here the system is said to be marginally stable. This is very important. That means when you put the value of zeta equals to 0, or if you design a system having zeta 0, the system is said to be undamped, and the output of the system is marginally stable, or you can say it has oscillations with constant magnitude. So note down this point. This is very important point. Case number 4, when you put zeta equals to 0. Okay, now move on to case number 5. In this case, we are going to put the value of zeta in the negative aspect. That means, suppose if you take the value of zeta below 0, that means if the zeta is negative, that means it is less than 0, but it is more than -1. In this case, the roots of the characteristic equations, or you can say the poles of second order control systems, are complex conjugate with positive real part. Why? Because the moment you take the value of zeta less than 0, but it is more than -1, this particular term is going to be positive. So it will be like complex conjugate with positive real part. I hope this point is clear to everyone. So if you apply that logic, you will get this as an answer. See, the roots of the characteristic equations are complex conjugate with positive real part. And suppose if you try to indicate them on pole 0 plot, they are something like this. One pole will be available at this location and another one will be at this location. Now in this case, the response of the system is oscillatory with increasing magnitude. See, this is very, very important. See, the response of the system is oscillatory, and that too increasing magnitude like this. That means the response is not going to approach to its desired value. The response is continuously going to move away with respect to the desired value. Hence, the system is said to be unstable. That is important. That means the moment we have the location of poles on right hand side with respect to imaginary axis, the system loses its stability and it's shifted into unstable zone. This is very important, and that is the reason a system is said to be stable if the locations of the pole are on left hand side with respect to imaginary axis in the S plane or in the pole 0 plot. The moment location of poles of the systems are on right hand side of the imaginary axis in S plane or in pole 0 plot, the system is said to be unstable. This is very important. I hope this point is clear to everyone. Why the system response is unstable? Because see, if you try to plot the variation of output with respect to time, in this case, the response are oscillatory with increasing magnitude. The magnitude is not going to die out because here the zeta is negative, which is very important. So please note down this point. This is very important. So case number 5 indicate that at what point our system is going to be unstable. So the moment we put the value of zeta negative, the system loses its stability and enter into unstable zone. I hope this point is clear to everyone. Now let us consider the last case, case number 6, when we put the value of zeta exactly equals to -1. That means if the damping ratio is negative, then what will happen? Again, if you try to find out the nature of roots of characteristic equations, see, put zeta equals to -1, this particular term is going to be positive, and if you put zeta equals to -1, this particular term is going to be 0. So here the roots are real, equal, and positive. That is important. See, the roots are real, equal, and positive. And suppose if you are interested to indicate them on pole 0 plot or in S plane, they are going to be located at this particular point. And in this case, the system is said to be absolutely unstable. That is important. Absolutely unstable. Why? Because the locations of the pole with respect to imaginary axis are on right hand side. Hence, the system is unstable. That is important. So, finally, this is what our conclusion. See, if you take case number 1, where we have taken the value of zeta which is less than 1 and it is more than 0. So in this particular case, the location of poles are over here. That means they are complex conjugate with negative real part. The system is said to be stable. So here the system is stable because the location of poles are left hand side with respect to imaginary axis. See, then when you put zeta equals to 1, zeta equals to 1, case number 2. See here the nature of poles are real, equal, and negative. That is important. And again, if you see the location of poles with respect to imaginary axis, both are available on left hand side. The system is said to be stable. That is important. And the moment you increase the value of zeta more than 1, that means overdamped. Again here, the nature of the poles are your real, equal, and different. And if you see the location, they are with respect to imaginary axis on left hand side. The system is said to be again stable. Now the moment you put zeta equals to 0, that means undamped. Undamped. So zeta equals to 0. See, the location of poles are complex conjugate with 0 real part. That means they don't have any real part. Now the system is on the verge of instability. That means neither completely stable nor completely unstable. In this case, if you see the response, it is oscillatory with constant magnitude. That is important. And the moment, if you see case number 5 and case number 6, if you put the value of zeta negative, that means less than 0, the location of poles with respect to imaginary axis are going to shift on right hand side. See here, right hand side, here also right hand side. Now in this case, in both the cases, the system is said to be absolutely unstable. That is very important. So finally we conclude that by simply observing the location of poles of closed loop transfer functions, or simply by identifying the location of roots of characteristic equations in the S plane, we are in a position to make a comment on system stability. If the poles are on left hand side of imaginary axis, the system is said to be absolutely stable. If the poles are on imaginary axis, the system is said to be marginally stable. And if the location of poles are on right hand side with respect to imaginary axis, the system is said to be completely unstable. This is very important. So I want everyone to please note down this point. This is very important. And based on these final conclusions, you may have various types of numerical on gate. Maybe theoretical questions or maybe numerical type questions. So case 1, 2, 3 are stable system. Case number 4 is marginally stable. Case number 5 and 6 are absolutely unstable system or unstable systems. This is very important. Please note down this point. What are the cases which we have discussed so far? This is what our final conclusions. And this picture indicates the variation of response, how the response is going to vary for each case. For case 1, the system is underdamped. For case 2, when zeta is 1, system is critically damped. Case 3, when zeta is more than 1, system is overdamped. This response is sluggish, slow. For case 4, when zeta is 0, undamped, oscillations with constant magnitude. And case 5, when the zeta is less than 0, that means negative, the system is unstable. Response is oscillatory or oscillations with increasing magnitude. This is very important. So case 1, case 2 and case 3, these are stable system. Case 4, marginally stable, undamped because zeta is 0. And case 5, system is unstable. Oscillations are continuously increasing with magnitude. This is very important. And this figure indicate all those responses in a single figure. So when, if you put zeta equals to 1, it is like critical. This is zeta equals to 1. The moment you increase the value of zeta, the response goes on delaying, or it goes on sluggishing. See, zeta is 2, this is zeta 2, and zeta equals to 4. See, this is going to be zeta equals to 4. More sluggish response. The response will take much time to reach its desired value. And the moment you reduce the value of zeta less than 1, 0.5, see, oscillations come into picture. See, if you put zeta as 0.1, highest possible oscillation you will get. This is for zeta equals to 0.1. That is important. So today we will stop at this particular point. In the next class, we will start one of the most important topic of control system, that deals with how to find the stability of system using Routh-Hurwitz criteria. What is Routh-Hurwitz criteria and how that is applicable to find the stability of the system. But whatever the points which we have discussed in today's class, that is very important as far as gate portion is concerned. And I request all of you to please revise them very carefully before appearing for gate exam, because this portion is very important. What is the effect of zeta on the performance of second order control system? Thank you.